Hey everyone, this will be the last video that we'll be discussing in Unit 3. We'll be discussing homeostasis and feedback. This section of the unit is pretty straightforward, so I hope you find ease with it. But let's just jump right into it. So our body has to be able to monitor its internal conditions at all times. And so this could include our internal temperature, hunger levels, water levels, blood pressure, you name it. It involves a lot of different things. Across all boards, across all different conditions that our body has to maintain, we have this thing called set points. And what set points are is that they are values for various physiological conditions that our body tries to maintain. Within our set point, we can have a normal range. So a set point is a specific number, whereas a range is a range of numbers that this number can fluctuate between. And so, for example, let's talk about body temperature. Our set point for our internal body temperature is going to be 98.6 degrees Fahrenheit. That is the ideal condition for our body to be in. However, that's not always the case. And so our normal range is going to be somewhere between 97 degrees and 99 degrees. And so our body can operate pretty well within this range. However, if we start dipping into 96 degrees Fahrenheit or lower, things get bad. If we start dipping into 100 degrees Fahrenheit or higher, things get bad. No bueno. We want to stay in between this range. Good. And this range, this normal range and this set point is going to be different for various functions like blood pressure, water levels, hunger levels, etc. Homeostasis is the state of being relatively in stable internal conditions. Let's think of the word balance when we think of homeostasis. We're constantly trying to get this to just be equal. However, it's very difficult, and so we'll sometimes see it tilt one way or the other. Our bodies are able to maintain homeostasis through feedback loops. Feedback loops. I should also highlight homeostasis. And balance. Keyword balance. And so whenever our organisms like us detect a stimulus, we have to respond to it. And that stimulus is going to be, oh, this room is hot. Oh, I'm hungry. Oh, I'm thirsty. Oh, I need to go to the bathroom. We have to respond to that stimulus and act on it in order to maintain homeostasis. We're going to have two different types of feedback loops that we're going to talk about, negative and positive. But before we get into that, there's a couple terms that we should normalize before we go into this so that we can understand what's going on. So the first thing that we're going to talk about is a stimulus. A stimulus is a variable that will cause a response. For example, your stomach might rumble. That's a stimulus. Tummy rumbly. Yikes, I can't believe I wrote that. Tummy rumbly. Your stomach is hungry, and so your body's telling you to go eat. We're going to have a receptor or a sensor. Sensory organisms that detect a stimulus. This information is sent to the control center, the brain. And so your receptor in this situation is going to be your tummy, your stomach. He's going to tell you that you're hungry. The effector is going to be that muscle or gland that's going to respond. And so I don't remember what the specific muscle is, but that rumbly part, what causes the rumbly is the effector. Oops, I'm sorry. That's not true. Your rumbly should be the response. Oops, can't even type rumbly. So the response is going to be the changes, whether it increases or decreases the effect of the stimulus. So if you're hungry, your stomach is going to tell your brain's going to tell its stomach, okay, start doing the rumbly. Your tummy's going to start doing the rumbly, and you're going to get up and be like, okay, I need to respond to this and go eat something. I hated that example I just used. Just kidding, I loved it. So we're going to talk about our first feedback loop, which will be negative feedback loops. Negative feedback loop. This is the most common feedback mechanism. This type of feedback is going to reduce the effect of a stimulus. So if you're hot, it's going to make you feel cold. If you're cold, it's going to make you feel hot. It's reducing the effect of the stimulus. And so some examples will include sweat when it's hot, blood sugar rising or lowering, or your breathing rate if you go on a run. So let's use Patrick Star as an example. Let's say Patrick Star is trying to maintain his internal body temperature. However, the first stimulus he might face is heat. The receptor that's going to activate is the temperature receptors in the skin. That's going to tell the brain. The brain's like, okay, initiate the effect, which will be sweat. And the response will be the actual sweat. So the effector, the sweat glands are going to start producing sweat, and Patrick is going to start sweating. Okay, but what if Patrick gets cold? The temperature receptors in the skin are going to be like, yo, it's cold. And so it's going to tell the brain, and the brain's like, okay, muscles, do your work. And the muscles are going to start contracting violently, and it's going to cause Patrick to start shivering, which is going to increase his temperature by generating heat internally. Whereas the sweat is meant to help Patrick cool off and go back to being happy. And so, ideally, sweaty Patrick would become happy Patrick, and shivering Patrick will become happy Patrick once the internal body temperature goes back to normal. This is the same thing with insulin. We can have two routes. Our set point is going to be somewhere, is going to be 90 milligrams over 100 milliliters of 90 milligrams of glucose per 100 milliliters of blood. And so that's the set point that we're trying to maintain. And so, for example, let's say we eat a cupcake. The stimulus is going to be the cupcake. It's going to cause our blood glucose levels to rise. Beta cells in the pancreas are going to release insulin to the blood. That insulin is going to cause the liver to take up glucose and store it as glycogen, which will then cause blood sugar levels to decline and go back to normal. Okay, but what if you don't eat for a while and your blood sugar goes low? So our pancreas, in charge of maintaining our insulin levels, is going to start releasing alpha cells, which are going to break down glucogen that is stored in our liver, and it's going to cause our blood levels to rise and go back to our normal homeostatic set point of 90 milligrams of glucose per 100 milliliters of blood. Next, we're going to have a positive feedback loop. This type of feedback increases the effect of a stimulus. So some examples of a positive feedback loop is going to include child labor, blood clotting, and ripening fruit. And so what I like to think of when I think of positive feedback loops is when you get a snowball, you roll it from the top of a hill, and it rolls down a hill, and as it rolls down, it gets bigger and bigger and bigger and increases in size. So the example that we're going to talk about is childbirth. And so how do we push a baby through the cervix? So our stimulus is that our water is going to pop. We need to push this baby out of the cervix. Our receptor is going to include the nerve cells in the cervix sending signals to the brain. The effector is going to be the pituitary gland releasing oxytocin, which is going to help with, which is going to start stimulating a response right here. Which this oxytocin is going to do is going to cause contractions, and that contractions are going to intensify and intensify and go around and go around and get worse and get worse and get worse and get worse until this baby goes out of the womb. There are many different ways that our body can may not able to be regulating its homeostasis in certain parts. So it could be able to regulate internal temperature, but not blood sugar levels. And so this can be caused by genetic disorders, if you abuse or use drugs, or you're in an intolerable condition like extreme heat or cold. A disease is when the body is unable to maintain homeostasis. So for example, when we have cancer, we cannot regulate our cell growth, and so our cells are going to constantly divide and divide and divide and divide and divide until we form a tumor cell that could either become malignant or benign. And then with diabetes, and that's when our body cannot regulate blood sugar levels, and we need insulin to help us regulate that. And so how does this all relate to cell signaling as a means of homeostasis? In order to maintain homeostasis, cells have to be able to communicate with each other. They need to be transparent. They need to be able to get information across of each other. If something's gone awry or going wrong, it's that cell's job to let the rest of the body know, because they're all in it to win it. They all want to survive. All the cells are working together to keep this living organism alive. And so this communication is going to happen through signal transduction pathways. And we'll be talking about how we are going to connect homeostasis and signal transduction pathways through FRQ questions.